In this section, we'll be writing functions of real-world applications. So let's get started. The first one, we want to write a function that represents the number of gaps in a fence with n number of fence posts. Okay, in problems like this, it's actually easier if we start off by drawing a picture. This is actually a pretty famous problem. It's called the fence post problem, and you'll see why in a second. So let's say we have some fence posts with some gaps in between. These little dots are gaps. I don't know why I'm using them for gaps, but these are fence posts, and we have gaps in between. So if we have an n number of fence posts, it's going to be the generalization of this. So we're going to have f of n is going to be our function. And let's just look at what we just drew here. We have 4 fence posts. How many gaps do we have? We have 3 of them. What if we had 5 fence posts? We would have 4 gaps. What if we had 6 fence posts? We would have 5 gaps. What if we had 7 fence posts? We'd have 6 gaps, and so on and so forth. So you can see that whatever the number of fence posts is, we're going to have 1 less gap than fence posts. So if we have n fence posts, the generalization of it, we're going to have an n minus 1 number of gaps. And this actually occurs for any type of fence, or it actually has a lot of applications more than fence posts. But f of n for this function, for this application, is going to equal n minus 1. So no matter how many fence posts we have, we're going to have 1 less number of gaps, which makes sense. You know, you can ride down a highway and look at a bunch of fence posts, and we'd have, or telephone poles, and we'd have 1 less gap than we do fence posts. Okay, so think about that for a second, and we'll actually go ahead and move on to the next one. Let's say Peter goes to an amusement park. The amusement park charges $15 for admission. $15 for admission and $2 per ride. So $15 to get in and $2 for each ride you go on, which is kind of expensive. We want to represent Peter's cost as a function of his number of rides. So let's go ahead and define our variable x. X is going to be the number of rides that Peter goes on. Number of rides. So f of x is going to equal Peter's total cost. His cost is going to be a function, or it's going to be dependent upon how many rides he goes on. So most of this function notation is fairly intuitive. So let's see, let's write this, our total cost. Let's just write it in word form first, just so we can fully understand this. Our total cost is going to be equal to the admission of getting in plus the cost per ride times the number of rides. So this is going to be, in layman's terms, this is going to be what our function looks like. So we can go ahead and fill this in. Our total cost, we know, is f of x equals the admission. The admission is $15, so 15 plus the cost per ride, which is $2, times the number of rides. We defined our variable x as number of rides. So our function is defined as f of x equals 15 plus 2x. So we don't have to calculate all of this every time if we want to know how many rides you can cost given a certain budget. We can just plug in a number of rides and we can see how much that's going to cost. That's how effective it is and how useful functions are, especially in real-world problems. So they definitely make more sense when we're talking about real-world problems such as the cost of something. So let's look at a few more. Let's say Paul wants to build a house. The house is going to be 42 feet long, and the contractor charges $95 per square foot. So $95 per square foot. Okay. Paul needs to stay within a certain budget, so cost actually is what he wants to know here. We want to write the cost of the house as a function of the width of the house. Okay, so we're going to need to know a little geometry here. So our house, I don't know if it's going to be a square or a rectangle, but it's going to have some sort of dimensions. and we're going to have the length and the width. Okay, so we're going to have the length and the width. We're given the length here. The length equals 42 feet. The width is what we actually want to find out. So let's go ahead and label W as the width of the house. And let's label F of W as the cost of the house. This is important. He wants to know, he has a budget he wants to stay in. So F of W, the cost, is going to be a function of how wide the house is. Because he knows he wants it 42 feet long. He just wants to know, well, how wide can I make it and staying within my budget, given that the contractor charges $95 per square foot. So what we have here, our function F of W, which is what we want to know, the cost. We know that length times width will give us the area of this house. So the area is going to be length times width. All right, so we know that the cost is going to be multiplied by the area because it costs $95 per square foot. So the cost is roughly going to be $95 times A. Well, A is length times width, so our function is going to be $95 times length times width. So let's go ahead and generalize our function. $95 times, well, we know the length, 42 feet long, so 42 times W. And this is going to be our function. F of W equals 95 times 42W. And we're going to leave it like this, just so we can see the individual parts. We could multiply this out, but we want to see the individual parts because he's charging $95, so we don't want to lose that piece of information, just in case he thinks the contractor's charging too much and he wants to compare it to other contractors. He's charging $95 per square foot, and each square foot is given by the formula for the area of the house, 42 times the width. He wants it 42 feet long, so he can plug in this function various widths to actually get the cost of using this contractor. And we're going to leave it like this in case he wants to compare prices. We have a couple more applications to get to, and we're running out of time, so we'll do it in the next video. I'll see you soon.